Okay, so linear algebra, introduction to determinants. So we'll define what a 2x2 determinant is, see what the determinant has to do with solving systems of equations, linear independence, area, and matrix inverses. So we'll start with the definition. If you have a 2x2 matrix, as below, the determinant is AD minus BC. So down to the left, down to the right. So determinant of M1 is 2 times minus 3 minus 1 times minus 4, which is minus 6 plus 4, which is minus 2. Right, and we can calculate determinant of the second matrix the same way. It's 1 times minus 4 minus 2 times minus 2. So these two minus those two equals minus 4 plus 4 equals 0. Okay, so calculating the determinant isn't too hard. What does this have to do with solving systems into solving systems of equations into unknowns? So here's a system. We could write this in a number of different ways. We could write it as a matrix equation. Or we could write it in terms of vectors. Which is sort of asking if the span of this, if V1, V2 is in the span of AC and BD. But there's a couple different ways to write or think about a system of equations. So if we just want to solve this system though, right, I'm going to set it up as an augmented matrix AB V1, C, D, V2. How am I going to solve this? Multiply top and bottom, multiply the top row by C, bottom row by A, and then subtract the top row from the bottom row. And you get AC minus AC is 0. AD minus BC is AD minus BC. We don't know what that is. AV2 minus CV1. Okay, so this is the key. If AD minus BC is not 0, we can divide through on the bottom row by AD minus BC. That will give us our 1. We can clear out the BC in the first row and we'll get a unique solution. If AD minus BC equals 0, then whether or not there's any solutions depends on what this term is. AV2 minus CV1 equals 0 means we get a parameter and infinitely many solutions because the bottom row would be all zeros. AV2 minus CV1 not equal to 0 means no solutions because we'll have 2 zeros and then some number that's not 0. So the determinant is not 0, then there's only one solution. If the determinant is 0, then either there's infinitely many solutions or there's no solutions, depending on what's going on there. And that's what this little summary is. So here's an example. We can use an augmented matrix to solve this. What's the determinant of the augmented matrix? Well, let's set it up first. 2, 1, 6, minus 4, minus 3, minus 4. Remember the last column is the answers, the solution, and then the x1 column, the x2 column. So the determinant is minus 6 plus 4 is minus 2. So there should be only one solution to this. So if we reduce this, we'll multiply the top by 2 to get 4 to 12, and the bottom, we'll just leave it alone. Add the top to the bottom, you get 4 to 12, 0, 2 plus minus 3 is minus 1, and 12 plus minus 4 is 8. And we'll carry that over to here. Divide the top by 2 again to get 216, and multiply the bottom by -1, just a little bookkeeping. And now we can subtract the bottom from the top. So we have 2 minus 0 is 2, 1 minus 1 is 0, 6 minus -8 is 14, and 0, 1 minus 8. And finally, 1, 0, 7, 0, 1 minus 8. And we start with these equations, did the augmented matrix, reduced it, and we want to end with 2 equations, one for x1 and one for x2. So there's x1 and x2. So exactly one solution. Okay, what does a determinant have to do with linear independence? Well, how do we tell if this is linearly independent? We need K1 AC plus K2 BD, because that's V2 equals 0, has only one solution. K1 equals 0, K2 equals 0. That's what it means for the vectors to be linearly independent. So as equations, this is A times K1 plus B times K2 equals 0, and C times K1 plus D times K2 equals 0. So remember here that the K1 and the K2 now are the variables, they're the unknowns that I'm looking for. A, B, C, D are known constants. So this is becomes the augmented matrix like this. We already know from example 1, AD minus BC not equal to 0 means only one solution. And what is that one solution? Well, it's this one. Because 0, 0 is always a solution, right? 0 on the right hand. So K1 equals 0, K2 equals 0 has only one solution, means that K1 equals 0, K2 equals 0 has to be that one solution. So are these linearly independent? And they're not, you can tell, right? You can multiply V1 by 2 to get V2, but as a determinant, we put these things into a matrix, because when we want to solve for linear independence, what do? We take the vectors, right? And we took the matrix like that and see whether or not there's a solution. But if we know the determinant as a way to check whether or not something's linearly independent, we can just look at the matrix whose columns are the vectors we're interested in. We get -4 minus 2 times -2, which is -4 equals 0. So not linearly independent. They must be linearly dependent, right? And so testing vectors, we've mentioned this above, but we want to be clear about this, right? Testing vectors for linearly independence means we want that as a pair of equations it's that. As an augmented matrix, it's that, right? So these 3 things, you can look at them and think about, well, I've got 2 equations and 2 unknowns, and I want to solve it. One way to think about that, and then I use the augmented matrix to solve that. Or I've got 2 vectors, and I want to know if they're linearly independent. This is the only solution to that top equation, K1 equals 0, K2 equals 0. And then you set up this augmented matrix to check. So different interpretations of the same thing. Determinant and area. So let I and j be the standard basis for R2. So there's I, it's the unit direction in the x direction, unit vector in the x direction. J is the unit vector in the y direction. We have a matrix M and ACBD. Well, we know that MI, so V1 is the vector AC, because we've done that a couple of times. V2 is the matrix BD. If you're multiplying by these matrix, this multiplying by I gives you the first column, multiplying by J gives you the second column. So we'll just say this is V1 and this is V2. So what is the parallelogram defined by V1 and V2? Well, it's the addition parallelogram. I draw a line parallel to V1 out that way and a line parallel to V2 out that way, I get this parallelogram. And the claim is that the area of this equals AD minus BC equals the determinant of the matrix A, C, B, D. Okay, and that's going to take a little bit of showing. So we'll redraw this picture on the right there, down here. So we've got I'm going to draw it without the arrows, but this point here is the point AC. And this point here is the point BD. So this is just going to be some analytic geometry. And here's our parallelogram. We want to know the area of that parallelogram. One way we can do that is if I put a vertical line right through here and a parallel vertical line right through here and join these up, then this triangle here and this triangle here have the same area. So the area is, of course, base times height. Because if we take this triangle, stick it over there, we've got this rectangle. I can call this the base and that the height. Good. So area equals base times height. Base is easy to find. Base squared equals a squared plus c squared, right? Because you've got a nice right triangle right here, and this is the hypotenuse. Height is a little bit trickier. We need to find the intersection of these two lines, right? We'll call that point x comma y. And then once we know x comma y, we can figure out the distance from x comma y down to the origin, and that would be our height. So let's see. Okay, good. So we'll do a little calculation down here underneath this thing. This line here, we'll call that line 1. And it's perpendicular to the line that is drawn through AC. So the line through AC has slope C over A, because C is the y coordinate, A is the x coordinate. So line 1 must be y equals minus A over CX, right? Because line 1 is perpendicular to this line, so the slopes are negative reciprocals. Now line 2, I'm going to call this one up here, because we want to find the intersection of line 1 and line 2. Line 2 is parallel to this line through AC, so it'll have slope C over A, and it goes through the point BD. So it's y minus d equals C over A x minus b. And we want to find the point of intersection of those two. Which I have. Okay. So and how do we do that? Well, we know that I'm going to clean these things out a little bit. Line 1 is CY equals minus AX. Line 2 is, if I just multiply everything through by Y, AY minus AD equals CX minus CB. So I just took this thing, multiplied both sides by C, took this thing, line 2, multiplied both sides by A, and that simplifies my life a little bit. So take line 2 and multiply it all through by C to get ACY minus ACD equals C squared X minus C squared B. And I want to do that because from line 1, I know CY equals minus AX. So I get minus A squared X. Yep, minus ACD equals C squared X minus C squared B. Right, I replace the CY here with the minus AX. Great, so get everything with X's on one side, everything without X's on the other side. C squared B minus ACD equals A squared X plus C squared X. Right, bring this thing over to the right, bring this thing over to the left. Great, so what is X equal to? You factor a C out of the top here. So C equals C BC minus AD, there's our determinant almost, all over A squared plus C squared. Great. So we know that minus AX equals CY. So Y equals minus A over CX. So if I take this here and multiply it by minus A over C, that would give me Y. So Y equals minus A over C. So there'll be minus A BC minus AD all over A squared plus C squared. Great. So there is our X and our Y. So coming back up to my formula for my area, what's my height? Well, we'll do height squared because it's a little bit easier. But height squared is just X squared plus Y squared, right? You can put in a little right triangle there. X squared plus Y squared is the hypotenuse squared. So that's going to be X squared, which is C squared over A squared plus C squared times the quantity BC minus AD squared plus Y squared, which is A squared, oops, that's squared in the denominator, A squared times BC minus AD squared all over A squared plus C squared quantity squared. And if we gather all our terms together, we've got, well, the BC minus AD squared is the same, the A squared plus C squared in the bottom is the same. We'll just have an A squared plus C squared over A squared plus C squared squared times AD minus BC squared. And I switched the order on AD minus BC because it's squared, so it doesn't, the order of which, when you do subtraction, doesn't matter because the square will get rid of the square root. Great, so area squared equals base squared times height squared. Since I'm running out of space, I want to multiply this by this. So this is 1 A squared plus C squared times another A squared plus C squared over A squared plus C squared quantity squared. So that all cancels out. And the area squared is the determinant squared. So the area is equal to the determinant. So that's actually kind of nice. What it's saying is that there's a more general statement of this, which is true, which is the area of this is 1. The area of this is the determinant of AD minus BC. And in fact, if I take any area over here and the function maps it over here, the ratio of the areas of the area in the codomain to the area in the domain will be that number, will be the determinant. So the determinant is actually a scaling factor. It tells you how big or small areas get when they go from the domain to the codomain. Okay, so Ij are the standard bases for R2, M is this thing, V1 is Mi, and V2 is Mj. What's the area of the parallelogram? So there's I, there's J, and they form a nice parallelogram of area 1. So one of my vectors is 2 minus 4. So that's down here. That's the first column. So this is V1 equals MI is down here. The second column is 1, 3. That's this one, which is down here. Didn't choose the best. Of these things. So hang on a second. Let me think about whether or not I actually got that right. Okay, so that is good. That's where those things go. So we want to know, what about the parallelogram here? What's its size? This is area 1. This is area AD minus BC. This is area determinant of M, which is -6 plus 4. Remember, it's 2 times -3 minus 1 times -4. So that's a +4. So that's -2. So the area has to be 2. What is that minus sign doing? And the minus sign tells us about the orientation of the two vectors to each other. If you know the right-hand rule, it's put your fingers in the direction of the vector I, and then roll your fingers up towards J, and your thumb is pointing in with your right hand, and your thumb is pointing in one direction. Here, if you do the right-hand rule with V1 and V2, you put your fingers down in the direction of V1 and roll them in the direction of V2, you're pointing the opposite direction. So what we have here is, if you start at I and go to J, you go counterclockwise. If you go from MI to MJ, you're going clockwise, counterclockwise. This is clockwise. So the minus sign is telling us actually that we've reversed the order of the vectors, right? If you stand in facing the direction of I, J is to your left. If you stand facing the direction of MI, MJ is to your right. So that's what the minus sign is doing. So same thing here. I and J is standard basis for R2. Determinant of M2, or the absolute value of the determinant, tells us what the area is, and that's -4 minus -4 equals 0. So the area equals 0. So what does that mean? Well, here's I, here's J, and over in our codomain, I gets mapped to 1 minus 2, and then J gets mapped to 2 minus 4. They don't actually form a parallelogram because they're right on top of each other. So the area of 0 is the area of the trapezoid defined by, no, it shouldn't be trapezoid, it should be parallelogram, defined by V1 and V2, because they lie on top of each other. And so that's the connection between all of this stuff in example 7 and linear independence. Parallelogram. So MI and MJ, as long as they're linearly independent, they form parallelogram that has some area. If they're not linearly dependent, then they are then the area is going to be 0. And finally, the determinant matrix inverses. Remember, to find the inverse, right? We set up A, B, C, D, 1, 0, 0, 1, and we grind through that to find out what the inverse is. But what we saw back up in example 2 is if you actually try to reduce this, you end up with A, B, 1, 0, 0, AD minus BC minus CA. So if you do that first step of multiplying the top by C, bottom by A, and subtract, you should get this. So if this equals 0, no solution, unless of course both A and C are 0, but if A and C were 0, then you don't really have much of a matrix, right? Because you have a column of zeros there. So there's no solution to this. You can't find the inverse if AD minus BC is equal to 0. So if M equals AD, A, B, C, D is any 2 by 2 matrix, what do we have? The number of solutions to MV equals W. Well, if the determinant is not 0, you have 1. If the determinant is 0, you have 0 infinity. Linear independence, area of image, having inverse. The determinant can tell you a lot about all of those. So what's the connection between these 4 things? We'll call this property 1, property 2, property 3, property 4. Number of solutions to MV equals W. How do you check that? You check that by setting up right and solve. And that'll give you, if you get a parameter, there's infinitely many. And what we've shown is that if this determinant is not equal to 0, you get exactly 1 solution. Linear independence of vectors, you set up the same augmented matrix, except you have 0, 0 on the same side. So those 2 things are really tied to each other because it's solving the same augmented matrix. The area of an image not 0, well, that is property 3 is tied to linear independence, right? Linear independence means that your 2 vectors, A, B, and C, D, are like this, and you actually have a parallelogram. Linear dependence means that A, B, and C, D lie along the same line, and you have no area. So these 2 are connected because if they're linearly independent, you get an area. If they're not linearly independent, you don't. And M has an inverse, means looking at this set of equations. And that ties back to dealing with the augmented matrix. So these things are all tied together. Now, we aren't going to have to go up into higher dimensions, really, for what we need to do in differential equations. So that's about 2-dimensional things. We could figure out determinants for higher order things. So here's a 3 by 3 matrix. What's the determinant of that? So to find the determinant of 3 by 3 matrix, we set up a checkerboard, and we do a reduction. We take a particular row, usually the top row, and we say, okay, we'll take 1 with this sign times the determinant of that matrix. So the determinant of M is going to be +1 times the determinant of the matrix 4, 2, 2, 1. It's the matrix that's left after you get rid of the row and column that 1 is in. Then I take -0 times the determinant of the matrix that you get when you take out the row and the column that 0 is in, and that's 0, 2, 3, 1. Okay. So the matrix 0, 2, 3, 1. And then we take a plus sign with -2, which will be -2, determinant of the matrix you get when you get rid of the row and column that -2 is in, so that's 0, 4, 3, 2. So what do we get? 1 times the determinant here, which is 4 minus 4, which is 0, minus 0 times that determinant, minus 2 times the determinant of this thing, which is 0 times 2, minus 12. So the determinant is 24. Do all these properties carry over? Yes. I got a non-zero determinant. What does that tell me about this matrix? MV equals W has one solution. The columns are linearly independent. The matrix has an inverse. And then the question about area becomes a question now about volume. 3 dimensions, if this is I, J, and K, that actually defines the cube, right? With volume 1. If we map this into 3 other vectors, and I'm not going to try and draw the 3 vectors from this matrix, but if we get 3 linearly independent vectors sitting in 3 space, then we get some kind of 3-dimensional tetrahedral kind of thing, which I'm not going to be able to draw very well. But you get some kind of a volume. And the volume of that thing, the 3-dimensional object that has these things as 3 of its sides, that's going to give you a volume of 24. So that's some basics about determinants.